Hi, in the textbook Linear Algebra and its Applications by David Ley, there are mainly true false questions. We will give the answers for those questions. We use the fourth edition of this book. Today, you may find the new edition of this book. Questions in section 4.3, linearly independent sets, basis at page 214. Problem 21. A single vector by itself is linearly dependent. 4. If V is non-zero, then the set V is a linearly independent set. B. If H equals span V1 till Bp, then V1 till Bp is a basis for H. 4. Example, R2 is spanned by these three vectors, but these three vectors are linearly dependent. C. The columns of an invertible n times n matrix form a basis for Rn. Q. The columns of an invertible n times n matrix are linearly independent and generate Rn. B. A basis is a spanning set that is as large as possible. 4. Example, these two vectors form a basis of R2, but the set of these three vectors is also a generator set for R2. B. In some cases, the linear dependence relations among the columns of a matrix can be affected by certain elementary row operations on the matrix. 4. Elementary row operations do not affect the linear dependence relations among the columns of the matrix. Problem 22. A linearly independent set in a subspace H is a basis for H. 4. Example, the set of these two vectors is a linearly independent set of R3, but it's not a basis of R3. If a finite set S of non-zero vectors spans a vector space V, then some subset of S is a basis for V. Q. If F1 till Fp spans the vector space V, this says the column space of A equals V, where A formed by these vectors. Then the pivot columns of A form a basis of column space A equals V. C. A basis is a linearly independent set that is as large as possible. 2. See page 212. B. The standard method for producing a spanning set for new A described in section 4.2 sometimes fails to produce a basis for new A. 4. The standard method described in section 4.2 always produces a basis for new A. See page 211. B. If B is the echelon form of a matrix A, then the pivot columns of B form a basis for column A. 4. Example, A is this matrix. By these row operations, we get echelon form of the matrix A, this one, equals B. The power columns of B are these two vectors. Note that the third row and the fourth row of these two vectors are all zero. So these two vectors cannot span this vector. Thus, the power columns of B do not form a basis for column space A. Questions in section 5.1, Eigenvectors and Eigenvalues, at page 272. In problems 21 and 22, A is a n times n matrix. Problem 21, A, if Ax equals lambda x for some vector x, then lambda is an eigenvalue of A. 4. If Ax equals lambda x and x is not 0, then lambda is an eigenvalue of A. B, a matrix A is not invertible if and only if 0 is an eigenvalue of A. 2. If 0 is an eigenvalue of A, then Ax equals 0 admits a no-zero solution. This implies the determinant of A is not 0, so A is not invertible. Conversely, if A is not invertible, then Ax equals 0 admits a no-zero solution. This says 0 is an eigenvalue of A. C, a number C is an eigenvalue of A if and only if the equation A minus Ci times X equals 0 has a no-trivial solution. 2. These two equations are equivalent. D. Finding an eigenvector of A may be difficult, but checking whether a given vector is in fact an eigenvector is easy. 2. Because we can just verify this equation. E. To find the eigenvalues of A, reduce A to echelon form. Fourth, echelon form of A in general do not give the eigenvalues of A. Eigenvalues of an echelon form of A in general are not the same as the eigenvalues of A. Problem 22. A. If Ax equals lambda x for some scalar lambda, then x is an eigenvector of A. Fourth, for x equals 0, Ax equals 0. But x equals 0 is not an eigenvector of A. If V1 and V2 are linearly independent eigenvectors, then they correspond to distinct eigenvalues. Fourth example, these two vectors are linearly independent, but they correspond to the same eigenvalue, lambda equals 1. C, a steady state vector for a stochastic matrix is actually an eigenvector. 2. By those definitions of steady state vector and the probability vector. E. The eigenvalues of a matrix are on its main diagonal. Fourth example, the eigenvalues of this matrix are 0 and 2, are not on its main diagonal. E. An eigenspace of A is a new space of a certain matrix. 2. Eigenspace of A associated to the eigenvalue lambda is u A minus lambda I. Thanks for watching. Bye.